So the recording will be available on the OECM website after the fact. So if you have other teachers that could take advantage of this workshop, make sure you let them know about what we've done today.
I'm in a meeting.
So let's get started. And the goal of our workshop today is to have a look at how we can integrate coding in our long-term planning and do it in a very thoughtful way. The goal is not to learn how to code today, although we will be going and do some coding. The goal is to give you an idea on how you can integrate coding in your planning, where to integrate it and how to go about it, how to choose the proper tools to do coding, depending on the age of the children, their prior experience, and also the material that you have access to at your school. So this is what we will be discussing today. And I'm glad you're here. I'd just like to introduce myself. I'm Dominic Tremblay. I'm an Ontario certified teacher, and I'm also a consultant with ALP, and I'm also a Lego certified teacher trainer. In my other life, I love to play with Lego, which works very well with coding as well, because many of the Lego kits can be coded. So we will have a look at how we can properly integrate our coding in our curriculum. As you know, it's part of the Ontario curriculum in math right now in grade 1 to 8. They recently added it to grade 9, and it looks like it's going to be added to all the way to grade 12, as well as in science. So I think it's worthwhile thinking about how we can properly integrate coding as part of our curriculum. So you have my information there. If after the workshop you have more questions or something wasn't clear, make sure that you message me. You have my email, phone number, as well as my Instagram and Twitter handle, D_Tremblay, where you can see some of the ideas that I come up with when I work with schools, what we do in schools, so you can have a look at all of these fun ideas. I'd like you to take some time to let us know where you're from, what do you teach? So I'd like to have a little bit of a feel of our crowd today. And also, what subject do you teach? Do you teach in elementary school, in high school? Do you only teach math, or do you also teach other subjects? Because that would help me change my examples if necessary, based on your grade level and subject you teach. So before we start, I'd like to recognize the land. To acknowledge this land on which we stand is to acknowledge truth. To acknowledge truth is also to acknowledge connection and disconnection. To acknowledge connection and disconnection is to acknowledge the nations who care for our mother. To acknowledge our mother is also to acknowledge truth. To acknowledge truth is to acknowledge that truth is at the forefront of the conversation. And this is a quote from Monique Ora from the Oneida Nation. And I would like to recognize that today I'm broadcasting from beautiful Belleville, Ontario, which is the land of the Tyendinaga Mohawk Territory. So I would also like to recognize that, and I invite you to recognize the land where you are right now in Canada listening to this workshop. And I see already some people in the chat mentioning that where they're from. So I see Adriana is from Niagara, teaching elementary school. So if you want to keep telling us who you are, that's going to help me as well tailor the workshop to your needs. I would like to take some time to mention that this workshop is provided thanks to Dell Technologies. We thank them for making this workshop possible. Also, thanks to Advanced Learning Partnerships, ALP, which is a group of consultants providing quality PD. And also, this session is made available by OECM. So we love the partnership with OECM. And as you've probably seen on the website, we have many other workshops part of this Ontario Learning Network. This is just the first few ones, but keep checking the schedule. We have a list of workshops available right now, and this list is growing. So make sure you have a look at all of the workshops, and you also tell your colleagues about all of these workshops that we have for you. So ALP, as I said, is a group of consultants providing quality PD for teachers. And their values are that together we perpetuate trust. Together we cherish the value of people. Together, we realize opportunity, and together, we also serve with gratitude. So just for your information, we are recording this workshop. So it's important that you know that if you don't want your beautiful face to show up on the recording or your voice, you can turn off your cam and turn off your microphone. Now, we are a small group, so if you have any questions and you want to turn on your microphone, feel free to do so. But you can also ask all the questions in the chat. I love reading the chat, and it makes the workshop a little bit more interactive when you participate in the chat. So I will have some questions for you that will make you think. So I hope that you participate actively. If you've got some colleagues who might want to join us today, it's still not too late. They can always go on the website, quickly registered, and join us as well. So during the workshop, we recommend that you mute your microphone unless you have a question or a comment. If you want, we would love to see you, but keep in mind we're recording this workshop. Use the chat actively. You can stay engaged using the reactions as well. And if you want, you can private message me if you don't want everyone else to see your message, or you can private message each other. So today, we're going to have a look at coding, and why do we want to teach coding to students? Why is it so important, and why was it added to the Ontario curriculum in math and soon in science? Well, if you look at those stats, 65% of students today will work in jobs that don't exist today. So this is based on research, and when we look at ourselves, when we were kids, a lot of the jobs that we have now didn't exist when we were kids. I'm just thinking as like a social media digital marketer. These things didn't exist when we were kids, and they exist now. Working for a social media company didn't exist when we were kids, and they do exist now. So there are quite a few jobs that the market is evolving and that didn't exist at the time, but they do exist now. And also based on research, they've looked at 80% of the future jobs will require science, technology, and math skills. So skills in what we call STEM or even STEAM. And all of the jobs in STEM education, 71% of them will require computing. So it's very important that we teach those skills to our students to make them, to give them what they need to thrive in the market when they are looking for jobs or contracts or things to do as an adult. Now, if we look like closer to the students, why would they want to learn coding? Well, some of your students may want to create their own mobile app. And this is more and more possible as well. I've seen a lot of high school students create an app, put it on the App Store, and start making money as a student. I've seen students create Roblox game and start making money. And it's not always about making money. It's also about the fun of creating something, about helping other people. But I think it's pretty cool when we see students being able to create their own mobile app. Students can create more interactive websites. And as you probably know, websites like from the past, like from my time in the 90s and the early 2000s, were not very interactive. It was mostly content. These days, all the websites have some sort of interactivity. They often run using database. So to make those website interactives, yes, there are some tools that exist to create websites now, but to create this super awesome interactivity, you do need students with coding skills. And again, that's something that I've seen in high school, students starting their own little business, providing website services for other businesses in their community. So it's a way for them to, start a project, be a young entrepreneur, and possibly get a job in that field. Some students may want to learn coding to perform certain tasks using robots, and robots is becoming more and more popular. I've quickly introduced myself when we started, but something I didn't mention is I do a lot of work with the World Robot Olympiad, and I get to see this in action where students are solving problems and are constantly working with all of those global competencies that help them, find a problem, tweak their code to solve challenges that are part of a robotics competition. Now, you probably don't know, but a lot of the robotics competition also have an open category where they're not necessarily like just moving balls and bricks and stuff like that, but they're also creating robots that are useful for someone, helping someone. This should also be part of planning your coding in your curriculum. How can we use coding to help someone? Some of them may want to have a career in computer science, which would be awesome. Some of your students may want to analyze data. And if you look at the Ontario curriculum, grade 8, one of the things that is part of the grade 8 coding expectation is to be able to make sense of data. So be able to analyze data quickly and make sense of it. So that's something that your students can build and learn when they're doing coding. Some may come up with cool inventions. And this year, even despite the pandemic, I've been working with a lot of schools with students doing coding and using a bit of electronics, whether it be microbits or Arduinos or Raspberry Pi. And those students were building pretty awesome inventions, solving real problems. And I'm going to give you like a quick example. I had students who realized that the store owners in their community were so annoyed by having to remind people to wear their mask when they come in the store and also to use Purell. So what did they do? They use an alcohol sensing sensors, which cost almost nothing. An alcohol sensors is like a couple of dollars that they plugged on a microbit. And then whenever someone wants to enter the store, they have to use Purell, put their hands under the sensor, and then use a little motor to either open the door or not open the door. So they automated a process that was annoying for a store owner by using a sensor and by using code. So I think that was a pretty cool invention. They also used artificial intelligence to be able to use a webcam like I'm using right now to communicate with you, where it would determine whether you have a mask or not, and you would have to put your face in front of the webcam and it would open or not open the door based on the presence of a mask or not. So students can come up with those inventions, and it's become a lot easier with the advent of microbits and Arduinos, even with younger kids. I would say like grade 5, 6, 7, 8. It is possible to do those things using those microbits. They make things a lot easier. So when you plan your year for coding, keep these things in mind. Do I need microbits or not? And we're going to have a look at a lot of these tools, and you can decide what you need and what you want to do with your students. But I think it's important to better plan your year for you to know what's available on the market. Sometimes students will also use coding just to make their life easier. Like you probably have seen those thermostat we have in home, or like at my house, I have a garage door opener that's on the internet. So it determines when my car is getting closer and will automatically open the garage door. Or those OK Google or Alexa or Siri or Cortana that lets you ask a bunch of questions. All of these things contain code. So I invite you to get your students to think of, where do we have code in our daily life? They may not have written that code themselves, but to recognize that coding is everywhere. Now, let's have a look at computational thinking, because that's something that you're going to have to keep in mind when you plan your school year. Computational thinking, also called algorithmic thinking, it's all the mental processes that happens in your head when you're solving a problem. But the big difference with computational thinking versus regular problem solving is that the solution will be carried out by an information processing agent. Instead of being carried out by a human, it's going to be carried out by an information processing agent. Now, if you've done coding a little bit last year, because coding was integrated starting last year in grade 1 to 8 in Ontario, you've probably done what we call unplugged activities. And those are great. These activities don't require a computer. They're easy to start with. As an example, I could ask my students, what are the steps required to shoot this ball into the basketball? So what are the steps that I need to put the ball in the net? So students have to come up with a list of steps, and they realize they have to be extremely precise in what they're saying. One of my favorite video, and you can search for that online. If you search peanut butter and jelly dad instructions, it's going to come up with a video. And it's a dad that's asking his two kids to create a list of instructions to make a peanut butter and jelly sandwich. And the dad acts stupid on purpose. So if the kid says, take the knife and put peanut butter all over the piece of bread, the dad will not put peanut butter only on one side. The dad will put peanut butter on both sides and even the crust everywhere. And he will say to his kid, well, you asked me to put peanut butter everywhere. You didn't mention that it was only on one side of the bread. If the students say, put the knife in the jar of peanut butter, the dad will actually put the handle instead of the flat piece of the knife on purpose, just so that students learn and his kids learn to be more precise. And this comes a lot with quantities, quantitative data instead of just qualitative. Like peanut butter, how many grams or how many milliliters of peanut butter should I put on that piece of bread? What force should I use when I'm spreading the peanut butter? All of these things are important. At what angle should the knife be? This is all important. So when you have your kids give the steps to shoot a ball in a net, they have to provide a lot of information. Like what kind of force, what kind of angle will I give to the ball when I'm pushing it? A lot of students, like one of the first activity I had them do is do high fives. And I had to stop this during the pandemic just because they were touching hands and that's not good. But hopefully the pandemic will be over soon and we can start these activities again. But just the idea of having two hands meet to do a high five, you have to give instructions to two humans. That's extremely difficult, but that's awesome because students learn to be extremely precise. When I do that with students, and I will first act as the robot receiving the instructions, if they say, Mr. Tremblay, raise your hand, I'm going to raise it and not stop and just keep pushing. And they say, well, not that high. Oh, well, you never told me. Oh, you wanted me to go only 40 centimeters. And then when it's time to do the high five, I'll make sure that I don't put my palm facing the right way. So they have to remember to give me that instructions the right way. So all of these unplugged activities can be a lot of fun. I do a lot of them using Lego as well. As you know, I love using Lego. So I'll use a Lego base plate and we will do a little adventure game where I have a minifig and I have a treasure and maybe I have some obstacle and they have to provide me with all the instructions. And then the cool thing is one student's write the code, the other one has to test the code. So follow the instructions because that's also important. Act as the computer or the robot that's going to be following the instructions. So those are unplugged activities. They are a lot of fun. You can do them. Are they mandatory? No. Should you just do unplugged activities? No. You need at one point to move to an information processing agent because that's part of the definition. You wouldn't be doing computational thinking or algorithmic thinking if you are only doing unplugged activities. And I heard a lot of schools say, well, we have no budget. It's a pandemic. We will just do unplugged. And it's good to start with. It's awesome. But at one point, you need to move to being carried out by an information processing agent. Now, I want your participation right now. What would be an information processing agent? The first thing that comes to mind is a computer, obviously. But in today's society, we have way more stuff in our homes and school and surrounding that have information processing agent. As an example, my cell phone it's an information processing agent. It can process information using a chip on the phone. It is an information processing agent. Even my blender these days is an information processing agent. There's some code in the blender that creates different cycles depending on whether I want a smoothie or I want to make peanut butter or I want to make a soup. There's different cycles, and there's code that will manage the little motor for making all of these. So I invite you to write in the chat some ideas that you may have where we would have an information processing agent, some of the tools that we may have in the house. So some people say tablets, like an iPad or an Android tablets would definitely be an information processing agent. And I'm going to give you some help here, but I invite you to continue thinking because this is not all of them. So we have the computer, obviously, a robot, your microwave, your stove. More and more, they have electronics and they have code that will manage the little display and that will have different cycles, different things. A fridge. Yeah, you're right. Like a lot of the fridges these days, I've even seen those fridge where there's a webcam and it, remembers what's inside your fridge so you know what to buy when you go to the grocery store. Cars, obviously. Cars these days are connected. They get information about traffic. A lot of them have sensors to not hit the car in front of you, self-parking, self-driving. We're moving there. A remote control to watch TV, a smart TV, a doorbell. Yeah, especially with the doorbell with the camera that can recognize people, talk back to people. A Roomba, so cleaning your house. This also is an information processing agent. And students will realize that more and more, they're making what we call the IoT, the Internet of Things. So in your planning, make sure that you realize that you get your student to think about everywhere where we have code. All of these tools that are information processing agent, it's going to make coding way more relevant than the thing that I want to make sure is kids don't go, oh, yeah, coding. That's the little cat on the screen talking about Scratch, which is a great tool. But we don't want them to think coding is just that cat. And it's a cat that you move on the screen. Coding comes with computational thinking that will let us run everything that is around us. They need to see the purpose. Someone mentioned that the thermostat. Yeah, the thermostat in your house is an information processing agent. It determines if I'm at home or not, and it will change the temperature. If I'm away from home, what's the point of keeping the air conditioning on when I'm not here? It will use my location on my phone to determine whether it needs to run or not, the AC or the heat. My toothbrush, I was surprised. My toothbrush is on the internet and it collects data about my my brushing habit. Let me know if I am doing it long enough with the proper angle. It has like a gyroscope in it. Awesome. I love that. And students, if you can make them amaze and love all of the things that are around us, and at one point, they'll be able to create their own, start thinking about their own. That's why we had my introduction. And I do realize that some of you may be teaching grade 1, 2, 3, and they may not be to that point, but there are some robotics sets and coding sets that will let students start doing some of these, tiny little invention. Just as an example, one of the things that I did before I left teaching, because I was a teacher for 13 years in a small French school in beautiful Trenton, Ontario. And at the time, we were still using little Duotang for the attendance. So instead of being like computerized, students would need to would need to go to the office with this little Duotang and give it to the secretary every single day. And a lot of the teachers were forgetting to bring this to the office every single day. So they created a robot that would move into school, go in front of each door, ring a little bell to remind the teacher to bring the booklet. and it would have a little cart on the back. And it was using like, one of those little robots that they sell, pretty simple to code, something like the Dash for younger kids. This is the Cody Rocky. It doesn't matter which robot, but the robot was moving and they had a sequence to go to all the classroom, notify the teacher, feel with a sensor when the book was there, and then go to the main office with all the booklets. So see, even with students in grade 1, 2, 3, little invention like that can be a lot of fun. So we just looked at information processing agent. Now you will realize that the brain, the human brain, works very differently than a chip. So if we take a chip or our brain, they work very differently. And I'd like you to think, what are some of the differences? Some tasks are better performed by a computer chip. Some tasks are better performed by a human brain. Can you think of some of the tasks? And I see some of you even wrote the Fitbit. Totally. The Fitbit is an information processing agent. Yeah, so Adriana is writing that the chip will do exactly what you ask them to do. Chips are not that smart when you think about it. Chip will do what you want them to do. They will do a sequence, and even if the sequence is stupid, or if the sequence is missing information, the chip won't know what to do. A brain, a human brain, can make assumptions. And if I give, like if we go back to the peanut butter and jelly activity, the students who would read instructions that are incomplete or instructions that are not precise or do not include all of the quantities, the human could still make a peanut butter sandwich. The human would connect the dots, would make inferences, make assumptions, and complete the task. A computer with missing information won't know what to do. But computers are pretty good at doing some of the things. Computers can find prime numbers pretty easily. Computers can do calculations pretty easily. Now, think of drinking something. What I just did is extremely difficult to code with a robot. I don't know if any of you have done robotics, but coding a robot to bring a ball somewhere or a block or to bring the glass of water to my mouth at the proper angle for the water to flow in my mouth, that's extremely difficult for a robot to do. So much coding is necessary. I have students work for hours and hours trying to teach a robot to do a task like that. For a human, 2 years old can do it. 1 year old, they can bring food and water to their mouth. So as you can see, there's some tasks that humans are better and some tasks that computers are a lot better at doing. And that's important to discuss that with your students. You don't always need to be in front of the computer. You can have those great discussions about computational thinking and coding with your students. Now, this is a very important slide. Now, this shows you all of the skills and all of those mental processes that are happening when you are doing coding and when you're doing computational thinking. So let's have a look at them. And while we're working today, because at one point I want to bring you into some coding software so we can have a look at what we're doing, it's important to keep in mind those processes. So the first one is decomposition. A lot of the tasks that we give to students are quite complicated. When you think about it, even professional coder will decompose a task. Whoever created Facebook didn't program all of the features at once. Whoever created Instagram didn't create all the features all at once. Whoever created a game like Pokemon Go or Animal Crossings didn't program all the features. They split the program in little parts. As an example, if I was to program Instagram, the first thing I would want to do is maybe access the photo library. Okay, that's one step. Okay, now I can do that. The next step is to crop the photo. The next step is to apply a filter. The next step is to add a description. The next step is to tag a location. Each of these can be programmed separately. When you're doing coding with your student, what does that mean in your classroom, because we always want to go back, what does that mean in my classroom? Never wait until you're fully done with your code before pressing play. That would be a mistake. Always tell students, you write a couple of lines of code, you test it. A couple more lines of code, test it. It's very important. It helps you simplify the tasks. The second thing that students need to be able to do when they're coding is to be able to recognize patterns. Look at the data. Are things repeating, or things that comes back, or may not be fully repeating but are quite similar? You need to find those patterns, and it will make your coding a lot easier, especially in grade 3 in Ontario. They're supposed to start recognizing repetition, so a pattern and in a sequence where they would use what we call a loop in coding. Another important process of computational thinking is algorithms. Students need to be able to create the list of steps. And if you look right in grade 1, we start with sequence. So being able to write a sequence, and all those unplugged activities have to do with sequences. So we start quickly with algorithms with students. For those of you who are from my generation, you probably remember those amazing New Kids on the Block with their step-by-step song. Every time I think about algorithms, I go back to this song. It's playing in my head, step by step, ooh baby. So all of the steps that are necessary to solve the problem. Now, what's pretty cool is algorithms are also used in number sense and operations. So when students are doing operations on numbers, they need to use algorithms. It can be their own algorithms or a traditional one, but they're using algorithms, which is, the steps to be able to perform an operation. The next one may not make sense right now. I'm going to talk about it even more as we move in this workshop, and it's abstraction. And the reason it's difficult is abstract is something usually that students see as difficult. Abstraction is removing all of the details, all of the things that are not necessary. And let me give you a very simple example of that. And then later in this workshop, we're going to look at more complicated examples of that. In grade 1, even in kindergarten, one of the first things we have students do is to use a little robot, and we create a maze on the ground, and the students need to code their robots to move through the maze. Very kindergarten / grade 1 type of task. It's awesome because students use sequences, so it's amazing. But sometimes the maze have elements that are designed to distract the kid. They may have houses and trees and stuff that are used for decoration, but are not essential to the task. The task, the only thing I need to know is what is the path that will take me from point A to point B. Who cares about all of the other elements? If I know this path, I don't need to know that there's a house on the right. Not necessary. It's extra information. So when students are doing those mazes, they should focus on the important data, which is the path, and forget about all of the decoration around it. So they need to abstract the path that will bring their robot from point A to point B. Now, as we work more towards grade 6, 7, and 8, you will see that abstracting will mean going back to the original definition of something. Let's say I'm talking about drawing a rectangle. What are the things that are absolutely necessary to draw a rectangle? Well, a rectangle has a length and a width. It has 90 degrees angle. This is part of the definition of the rectangle. Who cares about the other stuff? Like the color of the rectangle, that's not important. The thickness of the line that makes the rectangle, who cares? So we get rid of the extra information and we focus on the absolutely important information. And later this workshop, I'm going to show you some examples that you can use in the classroom that are so close to students' daily life. And I've used them in the classroom and I found, oh, students now get it. They now get what we mean by defining something and getting rid of the extra information. The last two parts of computational thinking, the last two processes, happen when you are actually running your code. So when you're running your code, you're basically modeling and simulating, and then you're evaluating. And these two you will do in what we call an iteration. You will do more than once. Rarely will students' code work the first time. And that's very important for you in the classroom. Bring this idea that it's okay that your program doesn't run the way it's supposed to. Always make mistakes. I love making mistakes in front of students and thinking out loud what the problem is and how I can solve it. So I'm modeling how students should act when it's not working. As you probably know, in our new curriculum, we also have Strand A in Ontario, which is our social emotional learning. Well, coding can become very frustrating. I code a lot myself for school when I'm as a teacher, but I also code in my personal life to solve problems in my personal life. And sometimes I will code stuff that is, pretty intense. And sometimes you can be like an hour and a half trying to find that problem and that bug, we call them bugs, that bug that makes your program not work. And you have to be able to manage those emotions because it can become easily frustration. So working on social emotional learning will be extremely important. So even though coding is part of the algebra strand, you will definitely use and go and use all of the other strands when you're doing coding. It's not designed to be only in algebra. The only reason it's in algebra is because the same way as you would use an equation or an expression with variables and constant to define something, you're kind of doing that with the code. So that's why it is in algebra, but you will go and, use other strands like measurement. Like kids in kindergarten who do a maze with their robot, they need measurement. So you will use the other strands as well. So it's a great way to integrate all the strands as well. So what does the curriculum tells us about coding? If we look at our Ontario curriculum, and if you are from another province, I invite you to look at what we do in Ontario, because some provinces don't have coding, already in the curriculum, and see how you can still teach the way you teach, but also bring some coding, even though it's not officially in your curriculum. Because the goal is not necessarily to teach students to code. That's one goal, but the goal is also to learn through code, learn measurement, learn geometry, learn data management through coding. So if we look at the general expectation, the pretty cool thing is it's the same expectation from grade 1 all the way to grade 9, the same general expectation, which is to solve problems and create computational representation of mathematical situations using coding concepts and skills. So obviously students are doing coding. It does say it, but the idea is to either solve problem or create representations. So when your students are doing coding, they either need to be solving real life problem or challenges that you give them, or they need to be working on mathematical representations. And that's awesome. How do you represent fractions? How do you represent quadrilaterals? How do you represent triangles? How do you represent the average and the mean and all of these concepts that you have in other strands using coding? The goal here is not to do coding just for the sake of doing coding, but it's doing coding to learn other subjects in math. And when you look at what we're doing in science as well, in science, when they officially release the curriculum, you will see that the goal will be to learn science through coding, learn about light and sound and temperature using coding. So that's where sensors will become super useful as well. So By starting your integration of coding this year with math, when the new science curriculum will be available, it's going to be pretty awesome to be able to include some coding as well in science, and you will already have some of those skills. So I want to take a few minutes to go through the progression of learning from grade 1 all the way to grade 8, just so that we look at what's new in every year and start discussing how we can integrate that. And now you may say, well, I'm a grade 5 teacher. Why would I want to know what they do in grade 1? Well, most of the kids have never done coding. So even if you teach grade 5 this year, you will need to go through all of the coding skills and concepts that we do in grade 1, 2, 3, 4. They are necessary because you build on previous year. The poor grade 8 teachers last year who were doing coding, and they basically had to do grade 1, 2, 3, 4, 5, 6, 7 before being able to address the grade 8 specific expectation. And that's okay. Don't stress out. Let's say you're a grade 3 teacher and you can't get all of it done. That's okay as well, because we're slowly implementing the new curriculum. So in grade 1, and I like what I did with this PowerPoint, just because I'm highlighting what's the concept, the new concept with every single year. So in grade 1, we've already discussed it. We're working on the sequence. That's how students start with very basic algorithm. You're step by step. It's a sequence, and the events are happening one after another. You move forward, you turn left, you move forward, you go 20 centimeters, then you turn right. This is a sequence. Awesome for dancing. I love dancing robots. So if you teach grade 1 or any other level, why not start including dancing with robots? Have your robots dance. And I'm going to give you at the end an article from my blog where I actually did a full workshop where students were including dance as part of their robotics work and coding. And when I say dancing and robots are not necessary. They're pretty cool to have, but you can do a lot of this stuff on the screen with virtual robots or just with what we call sprites on the screen. Grade 2, see, we still have sequential events, but we add concurrence event. And even the idea of dancing is still true, because you can have 2 dancers. They are not necessarily doing the exact same thing, but there's some sort of synchronization. Like when you look at synchronized swimming or synchronized dancing, they're not doing the exact same thing, but there's some sort of harmony between what one swimmer and the second one will be doing. Now, if you decide to do that, I highly encourage that you get your students to work together to create those concurrent events. It could be 2 students coding separately and try to make this a synchronized dancing, or you could use one computer and control 2 sprites or 2 robots from one computer and trying to have concurrent events. Now, you can't do concurrent events by itself. You still need to include sequential events. In grade 3, this is when students realize that we need to use repetition, repeating events, things that come back all the time. And if I look at, the integration with science, there's a lot of stuff that repeats in this world. The phases of the moon, the cycle of day and night. So bring those events and try to include coding with that. Like, how do we take the cycles that we have in our daily life and try to include them in a loop or a repetition? In grade 4, we add nested event. And I think that's going to make more sense when we go in our coding software in a few minutes, and we start nesting one event inside another one. So that's part of grade 4, and I'm going to show you what we mean by that very soon. Grade 5, I love grade 5 because it's starting to include conditional statements, what we call control structure. And I'd like to get some participation in the chat here. When we're talking about controlled structures and conditional event, it's often called if, then, else. If this is happening, then do that, else do that. So you have two separate events. It's basically like having a why. You have your main program, and then if something happened, do this. If not, do that. So you have two options. And control structures and conditional can even have more than two. You could have 3, 4, 5, 6. As an example, if we go back to those inventions that the kid did this year, if the alcohol level is high enough, open the door. If not, close the door. That's a conditional statement that's purely grade 5. Now, does that mean you can only use it in grade 5? No, because as you can see, those descriptions include all of the previous concepts. See, we still have sequence and we still have all of the other type of coding, plus this is what we add this year. Another example, my thermostat in my house is a conditional statement. If the temperature is above my set temperature that I decided, then start the air conditioning. If it's lower than that, stop the air conditioning. That's a conditional statement. And my recommendation is don't be afraid to have students say conditional statements like this without necessarily having them code on the computer. Like, can you think of things happening in your house? And I invite you to write in the chat where you would have a condition like this. If my car is close to the house, open the garage door. If my car is not close to the house, keep the garage door locked. Can you think of examples in your daily life where we would have conditional statements like this? Structure where we control things. Because this is more than a sequence. We're actually, branching the sequence. This is what we get with those control structures. So I invite you to write some examples in the chat. I'm going to give you, I did an example, a project with the School for the Deaf in Ottawa. And amazing group. And they have in their schools, they have a greenhouse. And the problem is they were forced to go back home because of COVID. And they go, who's going to take care of our plants? So they work at a system that fully automate their greenhouse. So if the light intensity was below a certain level, then turn on the artificial light. If the light intensity, the natural light, is high enough, then turn off those lights. That's a conditional statement. One of the things, if the temperature becomes too high in a greenhouse, then start the ventilator, start the fans. If the temperature is lower, then stop the fans. They had a pump attached to a water container. If the temperature, if the moisture, the soil moisture become lower than a certain level, then start the motors. And we have some example here. If the oven reaches a certain temperature, hold the temperature. So stop the burner. And that's why your oven, if you put it at 350 Fahrenheit, your oven will start and stop because there's a control system. So as you can see, you make coding relevant to students. So if the humidity level in a dryer is low, then stop the dryer. That means your clothes are probably dry. Awesome, great example. In grade 6, we start to bring efficient code. And by efficient, we're going to have a look in a few minutes what we mean. But we mean codes that will run easily, that will take advantage of patterns. And by taking advantage of patterns, you don't need to add extra code. When I judge at the International Robot Competition, some students say, hey, Mr. Trombley, look, my code has 10,000 lines. And they're so proud of that. And to me, that's not a good sign. If your code is that long, that probably means you didn't make it very efficient. I often have students who show me long code, try to reduce the code to make it easier to read, but make it more efficient as well. Now, with the advent of super awesome computers, efficient code has kind of sometimes become less important because our computers are so powerful. But I think it's still important to think about limited resources because, you know, the chip in your toothbrush may not be as powerful as the chip in your Dell computer. So you do need in your toothbrush to write code that is efficient, to use the limited memory and limited bandwidth on that microchip to be able to, you know, do the task that the toothbrush is supposed to do. In grade 7, your students will start to use sub-programs. And sub-programs are kind of program on the side that you can call anytime. It goes very well with grade 6, where you start to make your code efficient. And in a few minutes, we're going to go and have a look exactly what we mean by that. And then in grade 8, I've already mentioned that, we start analyzing data. So there's a great connection between the data strand in your curriculum and the grade 8 coding curriculum, because, you know, the average and the mean and being able to see trends in data, there's a great connection between the grade 8 and that strand. Now, you probably know that a new part of our curriculum, there was a lot added last year, is mathematical modeling. And this has been implemented from grade 1 to grade 9, where students will solve real life problem by having, you know, messy problems that are not necessarily easy to solve. So mathematical modeling can be at the end, when the students create the mathematical model, could be done using coding as well. So again, there's another connection between coding and mathematical modeling. If the students create a model to determine how much it would cost to put flooring in a room, what they could do is create a program, a code, where you would enter information such as, you know, the length and the width of the room, the type of flooring that you want, the percentage of wasted material that you would have, and then magically it would give you the price. So using coding to create a mathematical model using variables and constants. Obviously, that comes at a little bit older age. So depending on what grade level you teach, you may not want to, you know, merge mathematical modeling with coding yet. Now, when we said efficient code, let's think about grade 6. In grade 6, we want to write efficient code. So we want to avoid repetition. Use those loops. Those are awesome. A second thing, look for patterns, things that are not necessarily repeating, but are quite similar. Use variables. By using variables, you make your code way more efficient than hard coding all of the values. And in a few minutes, we're going to go in a programming interface, and I'm going to show you how we make this code. We go from a very inefficient code to very efficient. Something that you will find in most coding languages as well, programming languages, is the idea of using a list or a table of values where you can enter a bunch of values. And just to give you an example of what I mean by that, when I'm judging at the International Robotics Competition, we have the challenge announced ahead of time, and students use a robot to solve the challenge. So let's say they have move this, move that, pick this object. So they have their algorithm ready. The day of the competition, we have a surprise rule, something that changes last minute. And I have students who hard coded all of the moves that their robot needs to do. Now, when it comes to surprise challenge, they quickly have to change all of their code because an object might be in a different location. And students who don't write efficient code, it's so difficult. They have to look at all of their code and see where they need to make changes. Students who are efficient at their code will have all of their moves in a list. almost like a little Excel file with all of their moves. When the judge, the chief judge, announce the change in rules, they'll just go, oh, I need to change this distance and this, and boom, it's done. And I've seen students go, Mr. Trombley, this is unfair. How could they come up with a solution that fast to your surprise rules? They must have known the surprise rule ahead of time. This is unfair. And that's not true. It's just because their code was so efficient that they just had to change a few things and boom, it was working. So we're going to have a look in a few minutes at how we can do that. We're going to use custom blocks or subprograms if you're programming in a text-based language, and we're going to use libraries. So I'm going to stop the PowerPoint, and I want to make it also something that is, authentic. So we actually use a coding language. So I'm going to start a coding language here. You're going to see that personally, I'm using MBlock as a coding language, which is a copy of Scratch, but with a lot of extras. Now, you don't have to use MBlock, but you'll see that's one of my favorite coding language for students in at least the junior and the intermediate division in your school. Not for primary, but for junior and intermediate and even high school, I love to use MBlock. Now, you could do something very similar in Scratch. As a matter of fact, when you look at this, this is practically Scratch. It is based on Scratch. Now, it's in French right now, so I'm just going to switch by clicking on the planet here, switch it to English. Here we go. Okay, so let's say I want my students to draw a rectangle. So students have to think, what's the definition of a rectangle? So the first thing we need to do is, you remember I said one way to be efficient is to use a library. So a library is often called an extension in most of the school-based programming language. So I'm going to click on extension, and there's one that is called the pen. And this one also exists in Scratch. The main advantage of MBlock is the quantity of extension that you get that you would not get in Scratch. So I'm going to add this extension. Now, I want to draw a rectangle. So we always start with an event. So I'm going to go when the flag is clicked. And now I want to start drawing this rectangle. So I'm going to go motion, move, and then turn 90 degrees. And then move, and then turn 90 degrees. And now I'm not going to be efficient. I'm going to show you how students would do it if they were not efficient. Okay, move, and then turn 90 degrees. And now I want the length and the width. So let's say I want to draw a rectangle that's 100 steps long, 50 steps wide, 100 steps long, and 50 steps wide. This is not a very efficient program. There's a lot of repetition here. So if you look here, and I do need to make sure that I put my pen down, and I'm going to erase the whole. So I'm going to use the pen extension to erase my entire board, put the pen down, and then I'm going to drop this. So if you look, it is working. It is drawing a beautiful rectangle. And if I want to change things, I could say, well, I want this one, instead of being 100 steps long, I want to be 200 by 50. 200 by 50. Now, this is 200 by 50, so it's 4 times the length compared to the width. Not efficient. What if I want to make this efficient? Well, the first thing that students will notice, and they notice this in grade 3, is that this and this is exactly the same thing. So how do we deal with that? Well, we put this in the trash, and we use under control a repetition. And I only need to repeat twice because there's 2 length and 2 width. So see, now my program will actually perform the exact same thing with a lot less lines of code. So already we've made this code more efficient. Now let's say my teacher is mean and he asked me to draw 5 rectangles and they all have different length and width. Imagine how long it would be for me to draw those 5 rectangles. And I could duplicate the code like this. Okay, this time he wants a 30 by 20. Okay, but even though I'm, duplicating the code by doing the right click, it's still a super long and boring code. That is not efficient. So how do we make this efficient? If you remember when I said efficient code is to use subprogram. So let me show you what I mean by subprograms, because this would draw a multiple rectangle. Let me add a last one. It would work. This is 3 rectangles. See, I have 3 rectangles all done, but it's not efficient. Let me get rid of this. Let me make this code efficient. So I'm going to create a subprogram or a personalized block. In MBlock and in Scratch, it's called My Blocks. And I'm going to go create a block, and I'm going to call this a rectangle. Done. So see, I love the way it's said. It says define a rectangle. This is my definition of a rectangle. So right here, I can define my rectangle. My rectangle is to draw this. So now every time I want a rectangle, I can call one. I've defined it once, and now I can call it. The problem if I do that is that all the rectangles will look the same. Okay, if I try this, it's going to draw a first rectangle and then the second one on top of it. They're both going to be 200 by 50. And even if I take some times to, move, I'm going to move between rectangles. I'm going to change. Let's say we're going to do this one starting at 0, 0. Great way to teach coordinate with your students. See, you have your coordinates here. So this is actually a feature that we have in MBlock that it's not included in Scratch. In Scratch, you could have your grid, but you would need to add it as a background. Whereas in MBlock, it's right here. So I'm a big fan of MBlock. And let's say I'm going to draw this one at 50, 60. So now I'm going to have 2 rectangles, and they're going to be drawn in 2 different locations. I have this one and this one. Now, as you can see, I do need to solve this because when it's moving, it's actually drawing. So I do need to put the pen up whenever I go somewhere. And it's going to put the pen down when it's drawing the rectangle. So if I try this now, so see, it's working. I have 2 rectangles, but they're exactly the same. So let's improve this definition. And you remember I said, when you want to write efficient code, use variables. That's what I'm going to do. So on the define here, I'm going to right click and I'm going to go and say edit. And you see here, I can add inputs, and inputs are like variables. I'm going to add 2 inputs. I'm going to add the length and the width. Like this. So now every time I call a rectangle, I can choose, let's say this one's going to be a 50 by 20. This one is going to be 100 by 10. So see, I can call the size of my rectangle. Now, if I try my code right now, it's still drawing rectangles that are 200 by 50. It is not drawing what I'm asking here. And the reason is, if you look in my code here, it still says 250. So when you're defining something, you need to use these variables. I'm going to move the variables corresponding to the length, and I'm going to move the variables corresponding to the width. See? So now I'm actually using the length and the width from the definition here. So I'm calling a rectangle. So it's not a loop. I'm not using a loop here because a loop would make them all the same. With a define, so a subprogram, and some variables, I can create rectangle that are different in size. See, this one is 50 by 20, and this one is 100 by 10. So I get to choose. And now I want more rectangle. It's easy. I can just add more rectangle. And let's say I can call here 60 by 30, another rectangle. And let's say I want this one at minus 50, minus 50. Initial position, and then I'm calling the rectangle. See, now I have 3 rectangles. So even if Mr. Trombley is mean at math, ask me to draw 50 rectangles, should be pretty easy because I can always just enter the values here instead of having to recode a rectangle every single time. Now, let me improve this because a rectangle has a length and a width. The 90 degrees doesn't change, so I won't make this a variable. But another thing that will change is the location. Where will this rectangle start? So I'm going to add, edit, and I'm going to add 2 variables here. 1, 2. I'm going to call this one the position in X and the position in Y. I'm adding 2 variables to my definition. So now, instead of putting the go to here, I'm going to put it here. I'm going to put the pen up here. So pen up, go to, and then I'm going to call, let me zoom out a little bit so we have a bit more space. I'm going to call the position X and the position in Y. Now look at the magic. Now, whenever I want to draw a rectangle, I don't need all of this stuff. I don't even need the pen up, the pen down. I don't need this. I just need to call rectangle and write my length, my width, my position in X and Y, where the rectangle is starting. Let's say I want to put this one at 50 and this one at 60. And let's say I want to put this rectangle at minus 50, minus 100. And now, boom, that easy. I want to add a rectangle, go under my block, rectangle, I just write a new definition. The actual size and position of the rectangle is called the extra information. Remember when we were looking at those processes of computational thinking, being able to see the extra and the essential information. The essential information is that a triangle or a rectangle has a length, a width, a position in X, and a position in Y. Those are the 4 information. I don't need to know the specific of each rectangle to code. I can write this code without knowing where the person will want their rectangle and what size they will want. I can just create a definition, and then I have a machine to create those rectangles. Efficient code. If you're teaching grade 6, grade 7, the idea of sub-programs and being able to do efficient code, that's extremely important. Now, starting in grade 3, 4, 5, what I use here with the repetition, that's part of efficient code for these students as well. So now see, I want to add one. I'm going to make a tiny one, 10 by 5. And I'm going to make it at minus 100, minus 120. And here we go. We have 4 rectangles. I have a machine to create rectangles. And now I could create a machine to create squares, a machine to create triangles. Actually, good students who are good at coding will create all of their own libraries like this. And whenever they need to, they're going to call those libraries that they created themselves. So if the teacher asks for something, it's going to be easy for them. They're just going to call their own blocks that they created themselves and use them. And that's how students in robotics competition or coding competitions can be ahead of the rest of the group by defining their own things like this. And at this point, let's see how easy it would be to add, let's say, the area of those rectangles. So I'm going to announce, say, and now I want to say, let's say the area So I would just use operation, multiplication. And what do I want to multiply to get the area of a rectangle? I want to multiply the length. And I don't think, I did choose multiply here. Multiply the length by the width. By the way, in coding, the star or the asterisk is considered a multiplication. So now if I try this now, after each rectangle, my Super Panda is going to announce the area. And let's say I want to do the perimeter. I would do the same thing. Say, and then I'm going to use my operators. And we all know that we need to add the length plus the width. And we need to multiply this by 2 because there's 2 length and 2 width. That's for the perimeter. So I'm going to add the length, the width, and I'm going to multiply by 2. See, this is one reason why coding is part of the algebra unit, because as you can see, I'm using variables to represent a situation here. So now if I try this now, my Super Panda is going to announce the area and then the perimeter. Here we go. This is 1,220. See how efficient and quickly I'm getting all of this information by writing just a few lines of code. And if you are interested in making it more user-friendly, you can always use a join. A join lets you put sentences together. So I could say the area of the rectangle is, and then just take these, right, this, like this. The area of the rectangle is, and I could do the same thing here. I'm going to join. Join puts text together. The perimeter of the rectangle is, and then I can join these like this. So now if I start my program, see now it's a little bit more user-friendly. It tells me what those numbers are. And I just want to add a rectangle. Super easy. Boom. Here we go. Rectangle. Now let's go back to the PowerPoint because I wanted to show you what we meant by, writing and coding efficiently. I use this coding language, but then when you're planning your school year, you're going to have to decide. There are different types of language. This is a language called block-based language, and Scratch is like that too, with text. So it's block of text. Now, there are different languages. If you are teaching with younger kids, I would go block icons. Scratch Junior, that I'm loading right now, would be an example of block with icon. So that would be an easy language to use for younger kids. It's called Scratch Junior. And see, there's no text. So it's block and icon. So let's say I want to make my super character move like this. And then my character is doing the code. So kids don't need to know how to read. Very useful in kindergarten, grade 1, when their reading skills are not there yet. Now, so that's icon. This is block with text. And the next step would be full text. So programming in Python. This is what professional programmer would be using in the business, would be Python, or things like JavaScript or things like C++. This requires a little bit more skills. What I like with mBlock is you can do block-based coding, but go and peek at the real code behind it. So students can slowly start to get acquainted with the text-based coding. So using mBlock, using Scratch Juniors are all options for you. Another great option that I recommend is Microsoft MakeCode. Microsoft MakeCode is also a great tool to teach coding. Let's say I choose the Minecraft or the Microbit or these robots here. What's great with the Microsoft product is that, let me put this in English. I just did a bunch of workshop en français. English, here we go. start. I'm going to give it a name. So this would be also block-based coding with text. So students would be coding like this. If I press button A, say hello, they can test their code here. So if I press button A, it's going to say hello, but they can also quickly switch to text-based coding right here in Python. So they can go back and forth with block and text-based. So in your planning for this year, that's going to be something to keep in mind. Do you want to do block-based coding, or do you want to do text-based coding, or are your kids too young and you actually need to do icon-based coding? And as an example, if you take Spike, which is a Lego product, and as you know, I'm a fan of Lego, that's also another option. There are so many options that you can use. Spike is a great way to do coding using Lego bricks. So they have Spike Essential, which is for younger kids, and Spike Prime, which is for older kids. But you see, in the Spike coding system, when you start coding, it says, do you want to code with icon blocks, word blocks, or Python? So depending on the selection, students can code their Lego robot with icon like this. Or if I start a new project, I could do it with word blocks, which would look like this. So see, this is blocks with words on them. And the other option would be Python, where students would actually be writing, text-based coding. So keep in mind, based on your level of expertise and what you feel your students can do, what would you prefer to do? Which type of coding? And before you purchase something or go on a website, have a look at what is available. Lego is kind of cool that they put all three of them in one interface. I'm going to give you also a copy of this website. This is only available in French, but I think you can still at least understand the tool and the grade level. So what I did is for the different primary, junior, and intermediate, I gave a list of recommendations. So just look at the first column and maybe the cost column and the platform that is required. So free, a little bit of money, a lot of money, a truckload of money, okay? And what devices can run them. And so those are my recommendations. So even though it's in French, because it's pretty easy to understand, and I think those tools would be useful to you. This is on the Ministry of Education website. It's under the long-term planning on the Ontario curriculum, but only under the French version. I wrote that part for the ministry. So feel free to at least have a look at the tools. Once you have the name of the tool, you can, Google the name of the tool and find more information about these tools. So these are my recommendations for primary, junior, and intermediate. Now, going back to this super PowerPoint, we've seen efficient code now. So we're going to have a look, and we're going to finish with the process of abstraction. How do we get rid of what is not necessary and focus on what is necessary? So the purpose of abstraction is to eliminate all of the unnecessary details. And these are the two examples I use in the classroom because I find them so easy for students to understand. The first one is with the Pokemon game. Like, a lot of your students have played Pokemon, either with Pokemon cards, with Pokemon Go on their phone, or Pokemon games on their Nintendo Switch. A lot of your students would know about Pokemon. Now, let's try to abstract a Pokemon. So we won't even be using a computer. We're going to try to abstract a Pokemon. So if I look at 3 descriptions of Pokemon here, I have a male Bulbasaur with a combat point of 123, an immediate attack called Vine Whip, and a charged attack called Power Whip. Okay, so that's one of my Pokemon. And your students who play Pokemon would know about all of these things. Let's say I have a cute male Pikachu with a combat point of 111, a immediate attack of Thundershock, and a charge attack called Thunderbolt. And I also have a female Squirtle with a combat point of 152, an immediate attack of Bubble, and a charge attack called Aqua-Jet. Okay, let's try to abstract this. In every definition, I have a gender, male or female. I have the name of the Pokemon, Bulbasaur, etc. I have the combat point. I have a picture. I have an immediate attack, and I have a charge attack. That's all I need to know. And this is true for all the Pokemon. My Pikachu has a gender, a name, a CP, a picture, an immediate attack, and a charge attack. My Squirtle also have all of these: a gender, a name, a combat point, a picture, a charge attack, and an immediate attack. And same thing with all of my Pokemon. So as you can see, defining a Pokemon is this. All of the details. Is it a Squirtle, a Bulbasaur, Dragonite? Who cares? What's important is what is included in the definition of a Pokemon. So if I were to code a Pokemon game, that's what I would need. All of the extra stuff can be added later. As you can see, we would create fields or variables for this information, and this can be added later. The cool thing is, let's say I start my game with 50 Pokemon available, and then I want to update my game. I want to add 50 more Pokemon. I don't need to add coding. I just need to add to the list of definition. So I'm abstracting the concept of a Pokemon. So I found this one extremely powerful in the classroom for students to define what a Pokemon is. And then I have them find things in apps and games that they use all the time and have them define those things. Who cares about the details? Let's look what makes this, what define this thing. Another example that I like with older kids, I use this one mostly in grade 7 and 8 when they start to have their own phone and they love to post stuff on Instagram. I have them define an Instagram filter. So let's have a look at some of those super filter that we have on our phone. So one of the filter we have is called Clarendon. And as you can see, this filter will increase brightness by 10. It will increase contrast by 15%. It will decrease shadows by 5%. It will increase highlights by 25%. And it will increase saturation by 12%. Now, if you take another Instagram filter, the Ludwig, this is what it's going to do. It's going to increase brightness by 13%, et cetera, et cetera. The Mayfair filters will also do different actions on the photo. Now, if we look at abstracting the concept of a filter, this is what it is. A filter changes contrast, brightness, shadows, highlights, and saturation. That's all you need to know. Who cares about how many percents for each of the filter? When I code my filter, this is what I'll need to include in my code. Contrast, brightness, shadows, highlights, and saturation. I don't need to find the numbers yet. See, all of the filters have the same 5 elements, things that we change. So now I have a definition of an Instagram filter. I want to create the Dominic super cool filter. I can just add the definition. The coder, the programmer, has already created, the filter. And then in the list of definition, I would put Dominic filter. I would probably need to put the name of the filter as also part of my abstraction. And then I would just put values for each of these things. And then boom, we would have a super filter. So now just, as you can see, we've just defined what a filter is. So when we get to the kind of thing we do in the math classroom, we've already done this activity for real in our coding language. In this case, I use MBlock. As you can see, definition of a rectangle, we need to know the length, the width, the initial position in X and Y, and that's it. So I've defined what a rectangle is. Now, can your students have fun and do more things? Yeah, totally. As an example, I could say, I want to define something else. I want to define in my rectangle, I'm going to edit, And I'm also going to add the thickness. Okay, I'm adding the thickness. See, it adds an extra variable. And now before I start drawing, I'm going to go in my pen and I'm going to set the pen size to, and I'm going to use the variable thickness. So now I can have some fun. My first rectangle, maybe I'm going to make it the thickness of 3. The second one, the thickness of 5. 1. Let's say this one, I'm going to make it, it's small, the thickness of 1. And this one, I'm going to make it the thickness, well, it's a pretty small one. So let's get rid of this. So now, if I try, I have all of my rectangles. And as you can see, they all have different thickness. This one has a thickness of 3, 5, 1, and 1. Now, if the thickness is not something important, you don't define it. But if it's something important, it's that easy to add something. Let's say I want to define something else. I want to add a new variable, which would be the color. That is okay. That's totally fine. I'm going to set the pen color to, and I'm going to drag my color. And now I can say, I want this one to be a color of 25. By the way, if you don't know, when you add a color, because that probably means nothing to you, when you add a color, colors go from 100 to 0. So I could come here and, know my list of color here, like this. Okay. So a color of 0 would be red. A color of 25 would be about green. So I can add colors. I'm just going to add random color here for fun. Okay. So now see, I'm putting so much information here, and I can run the program. And now each of these will be a different color. Now, the problem here is that I need to set the saturation, because right now, my saturation, if my saturation is at 0, all of them, or my brightness is at 0, all of them will show black. So I would need to set my my brightness and my saturation, my brightness to the max and my saturation probably to the middle. So I do need to do that as well before I do it. But as you can see, now you can control more easily what each of the rectangles will look like. So I hope you've learned a lot. Again, this was not learn how to code, but it was more like, what do I need to take into account when I want to integrate coding in my classroom? And hopefully the choice of a platform. Do you want to use robots or not? Do you want to use icon-based, text-based, block-based coding? And also, like, what kind of activity will I start with? I hope you can see now that you can use these activities. And how will I bring subject like decomposition and abstraction and patterns in my teaching of coding? And how can I integrate it with the other subject? This is what we were hoping to cover. And I hope this helps you with the integration of coding in your classroom. Just to finish the workshop, we do have a session survey. I'm going to put the link in the chat. Give me 1 second. So the link in the chat here, and I'm going to put here the slide. So when it asks you for the topic of PL, you can say achieving excellence. When it asks you who facilitated the workshop, you can say it was Dominic Tremblay. And the type of professional learning is a virtual online course. So if you have some time, I would really appreciate if you could fill out the survey. It helps us get better. And thank you very much for attending this workshop provided by Dell and by OECM and by ALP, all three together working to make this series of workshop. And give the link to your colleagues because we have more workshops coming and we would love to have great attendance for all of the workshop. Personally, I'm going to be teaching a French play-based learning coming in October. But if you look, we have so many different workshops available in English and in French on the OECM website. So thank you very much. And if you have any questions, I'm going to stay here for a few minutes, so feel free to ask them in the chat. I'm glad you enjoy the information. Again, I didn't want to make it a learn how to code because there are so many tutorials on that. I wanted to, have a look more at the pedagogy and the kind of messages that we are sending when we bring coding in our classroom. So thank you very much. And even though we had a small group, the workshop is recorded, so the recording will be available. So make sure that you tell your colleague about this recording and the other workshops offered by OECM. Thank you very much and have a great evening.